Okay, perhaps should I start, Gary? Okay. All right, welcome back everyone for this second day of a workshop on the challenge of compositionality for artificial intelligence. So yesterday we talked about general questions regarding the importance of compositionality for AI, and specifically its importance to build AI systems that can understand language and understand the world at large. And today we will ask specifically how we can build or whether current large language models can achieve the kind of compositional behavior that we observe in humans, and whether they can achieve the kind of compositional generalization that we see in humans. And if not, what might be the way forward to bridge the remaining gap. So we have already anticipated this discussion to some extent yesterday, but I think we'll hear more empirical evidence today from our wonderful panelists. So without further delay, let me introduce our first panelist, Dieuwke Hupkes. Dieuwke is a research scientist at FAIR, where most of her work centers around evaluating neural models of language and figuring out what they can teach us about language. She loves thinking about compositionality, grammar, and structure, and she's particularly excited about how neural models force us to refine our thoughts about all these things. So, Dieuwke, I will share your slides. 1 second. There we go. The floor is yours.
Amazing. Thank you. Thank you so much for the invitation. Talking about compositionality is definitely one of my favorite things, and I'm also very happy that I get to open today. What I want to open with, next please, is a shout out to many of the students that I've been working with over the years on this topic. Most of their work, I'm not going to discuss it today, but they have all really helped me shape my thoughts about what compositionality is, how it should be evaluated, and I want to give them some credit for that, because that is exactly what I'm going to talk about. I think it's also appropriate that I'm the first talk, because I'm not actually going to give you a lot of empirical evidence, but more share my thoughts about what we should actually evaluate when we're looking at compositionality in neural networks. Like, how do we know if a neural network is compositional? And on this little journey, I want to start with, next slide, a quote that I found in my master thesis last week, which I wrote when neural networks weren't actually practically very useful yet. So it was about hierarchical phrase-based machine translation. And this quote is, "In translation between other domains, logical languages, programming languages, compositional translation is almost trivially a sound approach, as the expressions of such languages are completely unambiguous and the compositional system according to which the meaning can be derived is known. Natural language has neither of these qualities, which does not only complicate the construction of a compositional translation system, but also renders the existence of such a system uncertain." Now, I don't think that at the time I envisioned that this is really going to be the thing that I was going to be thinking about for many more years to come. But I think it quite adequately expresses one of the very complicated things when it comes to evaluating compositionality in neural networks, which is that we actually have a lot of uncertainties about compositionality in language, not even thinking about neural networks. And we've already heard a bunch of examples of this yesterday. Ellison talked about the need for memorization of idioms and things. Gary gave a wonderful example of composing something as simple as a noun and an adjective, and how that composition function might actually be very intricate and depending on a lot of things. Raphaël told us that if you look at the principle of compositionality, formally that really doesn't mean a lot if you don't put any restrictions on what the composition function looks like, what it needs to compose, can it take into account context, can it not? And all these things make it incredibly difficult to discuss even compositionality about natural language, let alone when we want to evaluate if neural models can deal with it. Like, how do we even start with that? Now, how we do typically start with that, can you do the next slide, is looking at a synthetic data set, because that should be simple, right? We have a super compositional system, no exceptions, no things that need to be memorized, no ambiguities. So we should be able to figure out if a neural model can deal with that. And that's where many studies of compositionality also start, because you can really isolate compositionality from the rest. But actually, already in that case, there are a ton of questions that you can ask that are really not as straightforward as you might think. Like, intuitively, I think we all have this understanding of what compositionality is, right? But now imagine that you build a data set that you think is super compositional. It can only be solved if you really understand the underlying system. You split it randomly. Very often, your model is going to have a very good score on the test set. Then you split it in a different way that, given the system that you've generated, like if the model really understood that, it shouldn't really be such a problem. And all of a sudden, your scores just drop. Now, what is the difference between those two cases? Like, also in the first case, the test set contained examples that were unseen. So the model must have composed something to get to answers there. So what is the difference between this first case and the second case? Why do we call some strategies compositional and some not? Like, what do we actually mean when we say that a model is behaving uncompositionally? Now, what we did a couple of years ago, I, together with Bernard Dankers, Matthijs Mul, and Elia Bruni, is we went back to all these many pages that are written about compositionality in philosophy of language, and linguistics, and psycholinguistics. And we tried to come up with like different interpretations of what someone might mean when they say that a language is a learner, or like different compositionality properties. And we translated those into empirical tests that you can then apply to a model. Now, the first test, so I'm going to say first, next, Raphaël, that would be your cue to press. The first test, or the first property that we looked at was systematicity. This is like a quintessential compositionality property, which relates to recombining things that you haven't seen together into something new. Like the classic example for that I love is Szabo's example, that if someone understands what's a brown cat and a black dog, they should also be able to understand what's a black cat. The next thing that we looked at was productivity. Now, this is actually very similar to systematicity, but it has this notion of unboundedness. So while you can be systematic in a finite domain, for productivity, like this requires some sort of infinity. Often when people look at productivity, they look at like being able to go longer or deeper trees or things like that. Then the third one that we looked at is substitutivity. Now, under the principle of compositionality, if you take a phrase in a sentence or a constituent, there's that word again, or a word, and you replace it by something that has the same meaning, the meaning of the whole shouldn't change. And also this is something that you can translate into a concrete test. Like you can check if you swap out something for something else that has the same meaning, how does the model respond? Then the fourth one is one that's very related to processing, and we call this localism. And it relates to this idea that I think many people think about when they think about compositionality, that it has this idea that you should be able to iteratively apply compositions, like work your way down from the bottom of the tree and go all the way up. So in this particular test, we don't really check if the final answer is correct, but instead we check if the model actually does that iterative composition. Does that give you the same answer as when you let it process the entire thing? Now, the last one is a bit of an odd one out, but I really like it. It might be one of my favorite ones. It's an overgeneralization test, which is not like directly related to compositionality, but overgeneralization refers to this phenomenon that you overextend a rule where it doesn't actually apply. So I think the example that you might have all heard is a child saying goed instead of went, because it has learned that you can form the past tense of words by applying verbs by appending an ed at the end, and it applies this to the verb to go where it doesn't actually apply. And for humans and children, we take this as evidence that they have actually internalized that rule, because what they're doing is contradicting the data that they might have heard. And you can do a similar thing for neural networks. You can check what they're doing with exceptions, and if maybe they're sometimes actually applying a rule instead of memorizing those exceptions. And they do actually. I will not be talking about it today, but we generated some plots about that to see what happens during training, and I find it pretty intriguing myself. But so now that we're here with this synthetic data set, I think that for me, I mean, aside from that, I think like empirically speaking, it's really interesting to look at what these models are doing. And by formulating these tests, you get out a lot of interesting insights in the internal dynamics here. But for me, the most interesting thing about this work was that it really allowed me to think a lot about what compositionality means for me, or not allowed me, like it forced us to like be very concrete, like not only high level, but like what does this actually mean when you're evaluating in models? What I didn't like so much is that it was looking at synthetic data where there are no exceptions aside from the ones that we inserted in this overgeneralization test. And for me, for natural language, I think the thing that makes it really, really interesting is the fact that it's not only compositional, or that the composition, that it's so complicatedly compositional. So sometimes there are words that are used as idioms in some phrases. In others, they're not used as idioms. Sometimes the same phrase can be an idiom or not an idiom. And it is like, I think it's really difficult to overestimate how all over the place that is, and like how much being correctly compositional for a language also means that you need to know how compositional you need to be at what point. So for me, the ultimate goal is really to evaluate this in natural language. Now, how do we go about that? Next slide, please. We continued, of course, and we tried to formulate the same test also for natural language. I thought a bit on which of the tests I was going to show you today, because I cannot show them. I cannot show them all. We did systematicity, substitutivity, and overgeneralization. I was very tempted by the overgeneralization, but it takes too long to explain. So I'm going to go for systematicity because I think everyone will easily understand. Now, what did we do in our systematicity test? Next, we looked at several different setups also, but well, I'm trying to point with my mouse now, but that of course doesn't work because Raphaël is using the slide. Luckily, I gave this some colors. So we concatenated sentences. And then what we did is we swapped out the first conjunct of this concatenations. So we would give both these sentences that you're seeing here to a model, and then we would check if the translation of the second conjunct, so that would be the purple one, stays the same. Now, under a compositional system where we're really translating one sentence, translating the other sentence, translating concatenation, putting everything together, the second sentence shouldn't change, like the translation should stay the same. So in this way, this is an indication of how compositional the model is translating these sentences. Next, please. Now, what are we seeing here? Oh, sorry, the sentence disappeared. Well, I think you can all remember. Let me unpack this. So we considered three different setups, most that differed only in how much data models were trained on. We considered models trained on small data, well, small for MT standards, it was around 1 million sentences, medium data, and the full one, which was 70 million. Then in our, I'm pointing at the x-axis now, we had three different types of test sets. So we had fully natural data. So you can construct this data just by fetching sentences from the corpus, as you can imagine. But we also wanted to have some sentences where we had a lot of control in the test set. So the training is all done on fully natural data, where we had some control and we were like fairly sure that there weren't actually any ambiguities, and the first sentence did in fact shouldn't impact the second one. So those are the synthetic ones. The ones that, well, you used to see a minute ago on top were synthetic ones, because if I put the natural ones on the slide, there's no space for anything else anymore. So what we're seeing here, maybe we can do a little experiment, Raphaël. We can see if it's understandable if you do my mouse pointers. So we see on the left at the synthetic side, Yeah, excellent. We are so we see that in that case, like the full model actually has a fairly good consistency, but given how simple these sentences are, I would expect it to be really at 1. And the model trained on smaller data, like in like 60%, less than 60% of the cases actually outputs that it's actually consistent. So there's a lot of changes there. And this is in the synthetic data. When we're looking at the natural and the semi-natural data, these numbers are really much lower. So the second conjuncts are changing all the time, which is kind of intriguing, and I think not exactly what I had expected. But then again, I keep saying natural language is actually very complex. So maybe a lot of these inconsistencies were actually correct or warranted by the data. So I think the question that that you should all ask yourself when you're seeing this is indeed like, how much of this is actually problematic? Like, are these sentences actually incorrect? Now, to get an answer to this question, Verna and I did a quite elaborate manual analysis where we annotated around 1,000 sentences. I think she's going to think, why is Dieuwke saying 1,000? We annotated 900 sentences exactly, spread over the systematicity and the substitutivity examples, and we checked like what was happening there. Can you go to the next slide? I think probably one more. Yes, thank you, perfect. Now we're looking at the top row here. The other one is the substitutivity. And what we're seeing here is that of these inconsistencies, so I repeat, so the inconsistencies are the cases in which the translation of the second conjunct changes if we swap out the first conjunct. Of those, around 40% are errors. And what I mean by an error is that one of the translations was correct and the other one wasn't. Another 40% are rephrasing. So this means that they're both translations are equally correct. They're just not the same. There were also a bunch of cases where there were actually some ambiguities in the source sentence that we hadn't seen before. So, and changing the first sentence would like flip the reading of the entire sentence. So in that case, the sentences would like the two translations do actually have a different meaning, but it's not that one of them is necessarily incorrect. And then a small bit of it was also formatting. So this would be mostly like punctuation. There will be some comma in one sentence and there wasn't in the other. Now, I think that this plot very well illustrates like the mixed bunch that uncompositional behavior is when you are trying to evaluate this in a fully natural corpus. And what I would like to wrap up with is a bunch of questions that are going around in my mind after looking at this, after thinking what are the next steps for me to evaluate compositionality in neural models in natural language. Can you go to the next one? Yes, one more. Perfect. Okay, so the first thing, which I think is an important question, is how do we distinguish problematic uncompositional behavior from unproblematic uncompositional behavior? And here I'm mostly referring, well, for instance, to these rephrasings. So in some cases, you might say, I don't care if a model is rephrasing something or if it's assigning a different meaning. If you ask a human translator to translate something, maybe also it gives me a different translation from one day to another. Maybe if I'm chatting with someone and he's in a bad mood, he will interpret the exact same sentence that I'm saying differently than he did yesterday when he was feeling well. And maybe this is not so problematic, or maybe it is. Like this, I think, is really an open question that that we have to think about. Like, what do we actually want these models to do? Do we want them to have some default and only switch when there is evidence for that? Do we want them to just randomly pick one if there are multiple correct answers? Who knows? Then the next question that I'm thinking about is very similar, but it has a slightly different flavor, and is how do we distinguish needed uncompositional behavior from unneeded uncompositional behavior? And this one from the systematicity test, maybe it isn't as clear, but for instance, in this overgeneralization test, you see this a lot, is that sometimes models do overgeneralize, which means they're sort of too compositional. And in other cases, they don't. So how do we find this balance in evaluation when we're looking at natural language? And how do we distinguish these two things in our tests and when we are evaluating models? Then the third one, which relates also a bit to the question I asked yesterday at the end, is I found it kind of counterintuitive, or not counterintuitive, but it's like a little bit, leaves a little bit of bad taste in my mouth that these models trained on more data are more compositional, because this seems to sort of counter what we actually want. So an open question there is, I think, are the models trained on more data really more compositional, or is compositionality just not needed as much when we have a lot of data? And I don't know, I wanted to put this question because I would love to discuss this a bit more also in the panel afterwards. And then the last question, how compositional is language really? And can neural networks help us getting closer to that question, getting closer to actually understanding how language is structured? And that's one that for me is I'm particularly excited about. Now, I think I'm already over time. Apologies. I wanted to end with last slide, please. Thanking my two very treasured compositionality collaborators, Verna Dankers and Ellie Bruni, and of course, all of you for listening to me. Thanks.
Thank you very much, Dieuwke. All right, next up, we have, let me see, Linzen. Linzen is an assistant professor of linguistics and data science at New York University and a research scientist at Google. Before NYU, he was a faculty member at Johns Hopkins University and a postdoctoral researcher at the École Normale Supérieure in Paris. At NYU, Tal directs the Computational Psycholinguistics Lab, which develops computational models of human language comprehension and acquisition, as well as methods for interpreting and evaluating neural network models for language technologies. Tal, take it away.
So am I going to be able to just share my screen? Is that the
you should be able. There was an issue with Dieuwke, but you should be able to share the screen.
All right. Yeah, let me give it a shot. Okay. How does this look? Yeah. Okay. Great. I'm just going to do it this way. Well, so I'm going to sec here. Yeah. So I'm going to give a talk that's a little bit more, I guess, in the weeds than some of the other talks here. Hope that it will be still helpful for folks. So the question that we have for this workshop is whether neural networks for language can generalize compositionally, and my answer is going to be that it really depends. It depends on what kind of model you're evaluating. So if you're evaluating a model that's trying to predict the missing word in a corpus, which is the standard way to train language models these days, that's also referred to as pre-training, then it really matters whether you're evaluating the model on its original objective or on transfer to a new task like a semantic parsing task. I'll say more about that in the second half. And it also really matters what you mean by compositionality. So we're going to distinguish here two kinds of compositionality, lexical and structural generalization. And we're going to see that language models are actually very good at lexical generalization, which just means putting a new word in a syntactic frame that you're familiar with, but are not very good at structural generalization, which means interpreting a completely new syntactic frame that's made up of a composition of smaller syntactic frames. So that's what I'm going to say today. And the way that we can see that language models actually have quite a bit of compositional generalization abilities is by generating from them. That's kind of one of the things that we use word prediction models for. We have a probability distribution at each point in after we've generated n words, and we can just sample format and generate the n+1 word. So we can look at what the model generates and see whether it parrots its training set deterministically or any other way. So some of the tests that we did in this study, that's really mostly Tom McCoy, who was my PhD student, but did this project as an internship project at MSR. So he generated an enormous amount of text from GPT-2 as a big language model trained to predict the next word, and found some very interesting generations that suggest to me that the model has some compositional generalization ability. So this is just one of millions of examples you can find in this very long paper. So let's look at maybe example 11b, right? The Serats were lucky to have her as part of their lives. So the model generates a new word, Serats, that it's never seen before. And it not only does it generate it, but it knows how to use it syntactically. So it knows that it's a plural noun, and then it has to agree with the plural pronoun there, and so on. So it invents a new word, which is morphologically well-formed in English, and plugs it into a syntactic frame that it's familiar with and does it well. Another example is that the model is able to use verbs that it only saw in the passive voice in training in the active voice. So it generated the sentence, then they dry docked at Sasebo. It's something that you do with a ship. I don't know what that means exactly. But in training, the verb dry docked was only seen in the passive context, like Ostfriesland was dry docked in Wilhelmshaven. So this is another example of how the model is able to plug a word that it's familiar with into a syntactic context that it's familiar with, but it has never seen the word in that context in training. Another test that Tom did in the study was to measure how many of the n-grams generated by the model are novel, or n-grams the model did not see in the training set. And the larger the n-gram is, the higher the proportion of the n-grams that are novel. But what is even more interesting is that the model generates actually more novel large n-grams than humans do. So if you look at a corpus, you can split into a training test set. And if you measure how many of the 7 grams in the test set are novel, you see that the proportion is actually a little bit less than GPT-2. So the only way that you can generate novel n-grams is, of course, to generalize compositionally in some very basics, a minimal sense of the word compositional. So another thing that we can do with a language model that's trained to predict the next word is evaluate its sensitivity to syntactic rules by looking at the probability distribution that it assigns to words in syntactically complex contexts. So in this case, we give it the beginning of the sentence and we have it predict whether the next word should be a plural or a singular verb. And the challenge here is that the word cabinets here might lead you to think, oh, we need to have a plural verb next, but actually it's the word keys that matters here that determines that the verb should be were and not was. So if we have a symbolic compositional representation of the sentence, this is a very easy task to solve. But in deep learning models, we don't have such a representation. So we need the structures to emerge from training on network prediction. So let's see if it does emerge in language models. In this study, kind of an old study at this point, we gave the model 2 types of sentences that are drawn from a corpus, where, again, determining whether the verb should be plural or singular depends on parsing the sentence correctly. But we also gave it what we called colorless ideas sentences inspired by Chomsky, that are basically syntactically well-formed combinations of words that don't really make a lot of sense together. This example, the colorless green ideas that sit by the honor, sleep furiously, that doesn't make any sense, and there's really no reason to think that the sentence appears in the training set in any way. So you really, to get this right, you have to generalize an abstract rule to a new set of lexical items in this context. And what we found in our experiments is that the model did quite well. It didn't do quite as well on the colorless green idea sentences, the ones that are in the nonce panel here, as it did in the original sentences, but still it did much better than chance and only a little bit worse than humans. So that again shows compositional generalization abilities on the original objective. So the other part of this presentation will be on how well the model generalize when they have to transfer to a new task where there's a smaller amount of training data available. And for that, we're going to distinguish lexical and structural generalization. So what's the distinction that I'm drawing here? The lexical generalization is more like the type that we've seen so far, where you have a word, let's say in training, you've only seen the word Paula as the direct object of a verb. But then in the generalization test, you have to interpret Paula as the subject of the verb. But you know that names can be subject of verbs. You just haven't seen Paula specifically as a subject of a verb. A structural generalization test is where you have to take two tree snippets that you've seen in training and combine them into a new tree. So in this case, you know from your training set that noun phrases with a prepositional phrase modifier can be objects of verbs, and then in the generalization test, you have to interpret them as the subject of verbs. But you've never seen a noun phrase modified by a preposition in the training set. So we tested both kinds of generalization in a semantic parsing test. So in semantic parsing, it's like a sequence-to-sequence task. Basically, the goal is to take an English sentence and convert it into some sort of normalized logical form that abstracts away from all of the different ways of saying the same thing, basically. And then you can take that logical form and use it as input to a query a database or operate a robot or Alexa or whatever you need to operate. So we created this training test split where we strategically withheld from the training set certain combinations of primitives and constructions. So the word hedgehog was only seen as a subject in training, but then the generalization had to be interpreted as an object. Or we only saw the structural generalization case here, there were only noun phrases with 2 prepositional phrase modifiers in training, but then in tests, we had noun phrases with 3 prepositional phrase modifiers. So the results on this evaluation here, these are models trained from scratch. They're not pre-trained on word prediction first. So the results on the in-distribution test set in green, which are sentences that are similar to the sentences seen in training, were very high, but the generalization performance was much lower. And it was sort of varied based on the weight initialization of the model. If you zoom in on the outer distribution examples, but break them down based on structural versus lexical generalization, you see that lexical generalization is significantly better than structural generalization. So with structural generalization, we're close to 0% accuracy here. So in a recent work, this group led by P.F. Weissenhorn compared a number of different models on their structural generalization abilities on COGS, and basically they all do abysmally, except the models that have explicit structure in them, and the Chew-et-al model that I'm going to talk about in the next slide. So basically, all of the types of models, including the modification to transformers that Raphaël mentioned yesterday, don't really improve the model's ability to generalize structurally, but they do help with lexical generalization. And unfortunately, the way that we created the data set, a lot of the data set is the easier lexical type. So it looks like there's significant increase there, but it looks the structural generalization is still a significant issue. So what does help us generalize structurally? I'm not going to talk a lot about this paper, but what this paper, like a lot of other papers did, was a sort of a hybrid between a neural and a symbolic approach. What we do, Lindu and colleagues did, was to induce a grammar. Basically, we take we try to learn the grammar that generated this semantic parsing data set, and then we generate a lot of augmentation examples from that grammar and give them back to the deep learning model, to T5, as additional crutches, basically, as to kind of help it learn that it needs to generalize compositionally. So with enough push from a symbolic crutch, the deep learning model is able to generalize correctly, or at least better. I'm gonna skip this, but I can say more about why measuring lexical generalization is hard in kind of questions later. So why do these things matter? First of all, I think personally, I think that having more sample efficient models in pre-training is a useful goal for NLP. So it's true that when we pre-train a model on hundreds of billions of words, it can do the lexical generalization tests quite well. But I don't think that that's the best we can do. I think we can have models that learn from the same amount of data that humans learn from. This is kind of a plot that where I try to compare the amount of data that humans and neural networks learn from. You can't even see the amount of data on the human side because it's so the scale is so different, but here on the log scale. But basically, humans learn language from orders of magnitude less than language models, and I think it would be nice to have a language model that has this property. And the other reason it matters is that for those transfer tasks, like semantic parsing, we often have a very small fine-tuning data set. So this situation is very different from the situation that we have in pre-training. And if we're able to give models a compositional inductive bias, they will generalize appropriately even from a small amount of data. So there's this kind of famous by now example that we showed that natural language inference models generalize very poorly from their training data when the training data is, it's not even that small, but it's definitely much smaller than the pre-training data set. And one example is that the inference models that we tested basically were not sensitive to word order, kind of basic principle of compositionality. They completely ignored it. And they said, well, the lawyer advised the judge and the judge advised the lawyer basically means the same thing. I don't care. So that's why we think it's important to have this compositional inductive bias in fine-tuning and not only in pre-training. So to sum up, we showed that language models do much more than memorize, especially when they're evaluated on the training objective, on the word prediction objective. They can parse these nonsense, colorless, good idea sentences and generate novel text. So that's clearly compositional generalization. But of course, even n-gram models with enough smoothing can generalize new n-grams. So that's not exactly a high bar. And the ability of those language models to transfer their knowledge to new tasks to figure out that semantic parsing requires compositionality is a lot less impressive. And we saw that there's a fundamental distinction between lexical and structural generalization in this context. So for pre-training, it's actually not so clear that structural generalization is even going to be useful, because if you've seen billions and billions of English sentences, at some point you're going to have seen most possible structures of sentences, because humans just don't produce incredibly complex sentences. So you're just going to, it's not going to be that helpful. Lexical generalization is always going to be helpful because you keep coming across new words and new concepts. Someone's going to ask, what about in-context learning, language models of few-shot learners type of paradigm? The answer is that I don't know. I haven't done those experiments. My guess is that the biases would be more like fine-tuning than tests on the original objective, but that's kind of for future work. All right, thanks for listening and for the funders.
Thanks, Dal.
I'll stop sharing.
All right, so next up we have Stephanie Chan. Stephanie Chan is a research scientist at DeepMind, where her current work revolves around understanding the behavior and capabilities of machine learning models. She previously led R&D teams at AI-based startups in Boston, Barcelona, and Hong Kong, and she completed her PhD in neuroscience at Princeton University. Stephanie, would you share a screen?
I'm happy to go next. I believe that Ellie is next in the schedule. Do we want to stick to that?
Oh, sorry, did I? So who was next in the?
Ellie?
Oh, Ellie, sorry, yes.
Yeah, but it's all the same.
Okay.
I improvised yesterday in the schedule inadvertently, so it should become our custom of this time.
Okay. Well, we won't waste Raphael's very nice introduction of me then, and so I will just go next.
It's yeah, it comes up to you.
Okay. Can you see that? Sorry, can you see that?
Yes, we can.
Okay, great. Okay, awesome. Okay, so hi everyone, I'm Stephanie. I'll be talking today about our work on what you might consider a specific type of compositionality, a kind of role filler binding. I think Tal would call this semantic generalization. And we investigated this in the context and in the framework of in-context learning. And I'll be presenting our work on how the distributional properties of training data drive this intriguing phenomenon in transformers. And then I'll talk a bit about what the implications might be for compositionality and current models. These are my amazing collaborators. I want to thank them for all their contributions to this work. I also wanted to highlight that many of them, especially Adam, Andrew, Jay, and Felix, have thought very deeply and carefully about compositionality and systematicity. They've really strongly shaped my views on the subject, and so I highly recommend you check out their work if you're interested in these topics. Okay, So as preface, we have two very distinct modes of learning in neural networks. We have in-weights learning. This is the standard supervised learning that's slow, gradient-based. You need a lot of examples. And then we also have in-context learning. This is rapid. There are no gradient updates, and you can learn, as we've seen, from just a few examples. And hence it's also called few-shot learning, though it's a special case of few-shot learning without gradient updates. Omniglot, which is a standard data set for few-shot learning developed by Brenden, who will speak next. And normally this kind of fast learning only happens if we explicitly meta train for it. That is, we have to explicitly demand it from our models by training directly on specially designed few-shot data. And there's really awesome work by a lot of folks on how to achieve a few-shot or one-shot learning via meta training. But we've also seen in recent years that this kind of learning can emerge in transformers when you're training for a very different objective, for example, next word prediction. We see this in large language models and now also vision language models, which can perform in-context few-shot learning. So the question inspiring this research is, why can they do that? And there are more than a few hypotheses floating around. One idea is that transformer architectures inherently have an inductive bias towards few-shot learning. Our hypothesis was that the distribution of naturalistic training data itself, for example, language, is non-uniform in special ways, and that this is what drives the emergence of in-context learning in these models, or these types of models. So, for example, natural data is long-tailed. It's well known that words follow a power law or Zipf distribution. Natural data is also bursty. So in language, for example, words tend to appear in clusters rather than being evenly distributed across a corpus. And this is true not just for language. Here's a plot from Linda Smith, one of our favorite developmental psychologists, showing that infants experience object distributions in a similarly kind of long-tailed way. So our thought was that maybe these non-uniform properties and others lead language to act like an interpolation between supervised and few-shot meta-training. So very briefly, what do I mean by that? In the familiar standard supervised setting, items recur and are uniformly distributed, and also label mappings are completely fixed. This kind of data encourages and allows slow gradient-based learning in model weight. In few-shot meta-training, you explicitly train on the kinds of few-shot sequences you'd like your model to handle. So items differ on every episode, and label mappings are only fixed within episodes. And in language, we might have something in between, having properties that are reminiscent of both. And maybe this is what allows few-shot learning to emerge in language models, despite the models not having been explicitly trained for it. So in this work, we set out to test this hypothesis and also to test it in a domain outside of language to show that it's a general phenomenon. We modified the omniglot data set to control these properties and measure their effects on the emergence of few-shot learning or in-context learning. And I think that this work has a few implications. So beyond giving us a handle on understanding the behavior of language models, I think the most important implication here is that it helps us design or collect data sets to achieve in-context learning outside of language. So in our experiments, we have a causal transformer model that ingested sequences of image label pairs. And for these experiments, we use the omniglot data set, as I said before, which consists of different classes of handwritten characters. You might think of the image label mappings as analogous to word meaning mapping. And the first part of each sequence is the context, and the last image is the query. And the transformer is trained to minimize the loss on predicting the label corresponding to the final query image. Here's an example of what the sequences look like at training. We experimentally vary the distribution on these training sequences, as I'll describe later. And this particular sequence is what we call a bursty sequence, where image classes are repeated within a sequence, and the query belongs to one of those repeated classes. The image label mappings are completely fixed in all training, and this is in strong contrast to the few-shot meta training. And because of this, there are two equally valid ways for the model to solve the query prediction task. So over the course of training, it could gradually learn the image label mappings in its weights, or it could meta learn to refer back to the context, performing few-shot or in-context learning. Given that there are these two strategies to solve the training task, we can evaluate a trained model's ability to perform one kind of learning or the other. So the first kind of evaluation is for in-context learning, where we provide classic few-shot sequences. And here the two classes are randomly assigned to labels 0 or 1. And here, these are holdout classes. So these classes have never been seen in training. And so in order for the model to predict the correct query label, it has to use rapid learning from the context. And so this is the, I want to draw your attention to this because this is the compositional task in this experiment. The model needs to systematically apply the function, the binding of images and labels to new sets of omniglot images and labels that it hasn't seen before. We also evaluate in-weights learning of the classes. So we have sequences where the classes were seen in training, but the query doesn't appear in the context. So here, the only way for the model to predict the right label is to use the information stored in weights. I think I forgot to note the start time. I was wondering if I could get a note.
I didn't. Did you, Gary? I think it's okay. You can.
I didn't
Okay.
check.
Yeah.
Just do the best you can.
Okay.
Yeah. Yeah.
Okay. So what did we find here? So in our results, we found that transformers can indeed perform few-shot learning on the omniglot sequences. And this ability is enabled by increasing burstiness in the training data. So we varied the proportions of training data that were bursty or not. And you can see that if you increase burstiness, you get better few-shot learning. But you also see a trade-off where more burstiness also leads to worse in-weights learning. A second factor that encourages in-context learning or few-shot learning is the number of training classes. So you might consider this analogous to having a very large vocabulary. So this corresponds to that really long tail that you see in the distribution of language. And again, you see a trade-off. More training classes leads to better in-context learning, but also worse in-weights learning. We explored a number of other distributional properties as well that you see in natural data, and I encourage you to look at the paper and check these out. So in all the previous experiments, we saw a trade-off between in-weights and in-context learning. The model seems to only be able to do well on one or the other, but it's obviously useful for a model to have both kinds of capabilities. And large language models obviously do display both. So what kinds of training data might achieve this? So excitingly, we found that we could achieve both kinds of learning when we train on skewed distributions. And this is again something that we observe in natural data like language. So here are a few examples of these kinds of skewed distributions. We use a Zipfian or power law. The degree of skew is controlled by the exponent alpha in the denominator. And here is an example of the kind of skewed distribution that you see in natural language. But as I said before, this kind of skew exists in other kinds of natural data too. So when we trained on Zipfian distributions with various degrees of skew, we found that there was this sweet spot at the Zip exponent of 1, where we did indeed achieve in context learning as well as in weights learning of the common classes. This was one of my favorite results from this paper. And the intuition here is that the common classes are seen frequently enough that they can be memorized, while you also have this long tail of rare classes that induces an in-context learning ability in the model. Intriguingly, I don't want to put too much emphasis on this, but a Zip exponent of 1 corresponds approximately to the skew in many natural languages, including English. But with all that said about data distributions, we found that architecture still does matter. So when we trained on recurrent models on the exact same data, we did not achieve any kind of in-context learning ability. Here, the different lines are different hyperparameter sweeps. But I still want to emphasize here that even though we found that architecture does matter, it's not enough. You need the right kinds of data too. So to conclude, in this work, we studied a very specific type of compositionality in the framework of in-context learning. And we found that, well, I didn't mention this before, but large-scale models or data are not really necessary for this kind of behavior to emerge. Both were relatively small in our experiment. That's not to say that scale wouldn't be helpful in other scenarios. On the other hand, we found that certain distributions of training data did promote in-context learning. And these distributional features are present in natural language and also other kinds of naturalistic data. So this is an enticing potential explanation of in-context learning in language models. But I think it's also kind of like implied directive for how we need to design our training data in order to see in-context learning emerge in other domains also. And I want to draw a connection to work by, for example, Jacob Andreas and Ekin Akürek, showing the importance of data for inducing compositionality specifically. I think what's really exciting in our results is that you don't have to artificially modify or augment your data in order to see this emergence of in-context learning, but rather that natural data already has these properties. At the same time, architecture does still matter. So as I said, the data distributions could only elicit in-context learning in transformers and not in RNNs. And I want to draw a connection to Brenden Lake's work. He'll speak next, or later, so I'll only briefly mention it. But he originally showed that RNNs could not perform well on the compositional data set scan, while memory augmented RNNs could. And Adam Santoro pointed out in 2013 that memory augmented neural networks are helpful for meta learning because they have both long-term and short-term storage. And the short-term storage is stable and element-wise addressable. And we've seen in this work and in other work, for example, by Tal and others, that language models, that transformer-based language models can perform well on certain kinds of composition. And I can't help noticing that transformers have exactly these properties that Adam pointed out, as Desiderata in 2013. So, the kind of chain of reasoning is that transformers have these properties. These properties are useful for meta learning, and meta learning is useful for compositionality. Another set of work that I'd like to draw your attention to is the work from Anthropic, showing that transformers may be especially suited for composition because they kind of develop these like compositional operations internally. So finally, again, I strongly emphasize that architecture is insufficient. You need the right kinds of training data too. I think many others in this workshop have made this kind of point as well. That we've talked a lot about inductive biases, but you really need both the right kinds of data and the right architectures to induce these kinds of biases. And lastly, more generally, outside of thinking about compositionality, I think that we need to think more carefully in machine learning in general about data distribution, because the world isn't uniform and we need our models to be prepared for that. And secondly, non-uniformity can actually be an opportunity, as we see here, to enable these kinds of powerful and useful capabilities. Thank you.
Thank you very much, Stephanie. So next up, with apologies for the order mix-up, we do have Ellie Pavlick. Ellie Pavlick is an assistant professor of computer science at Brown University, where she leads the Language Understanding and Representation, or LUNAR lab, and a research scientist at Google. Her research focuses on building computational models of language that are inspired by and/or informative of language processing in humans. Currently, her lab is investigating the inner workings of neural networks in order to reverse engineer the conceptual structures and reasoning strategies that these models use, as well as exploring the role of grounded non-linguistic signals for word and concept learning. And Ellie's work is supported by DARPA, IARPA, NSF, and Google. Ellie, take it away.
Great, thank you. Can everyone see this?
Yeah.
Great. All right, so I guess I want to start by talking again about definitions of compositionality. I know everyone's kind of given their version of this, but I think the kind of way we do this research depends a lot on the details of the definition we're using. So we can, of course, use these more lenient definitions, the parties type definition, and I think people did a good job yesterday and in previous talks talking about why, at least I think that neural networks kind of trivially meet these criteria of being a function, the meaning of the whole is a function of the meaning of the parts. So I don't think there's a super interesting intellectual debate there. So I want to talk more about these kinds of stricter definitions. I think this is the type Gary was really referring to in his opening talk. So this is a quote coming from Fodor Volition in their very famous paper. And here this notion of compositionality has to do with the kind of intrinsic connectedness between certain kinds of concepts or thoughts or sentences, because these wholes are composed from the same parts. So we would say that, the sentence "the cat is on the mat" and the sentence "the mat is on the cat." These are obviously completely different. They have different meanings, but they're made up of the concepts cat and mat, the function on, and the kind of roles, the argument roles within on. So this definition is the kind that is often kind of in line with the traditional linguistic models like Montague and Chomsky. And this is the one that is not obviously compatible with neural networks, right? It may or may not be, that's the open question. So I think this is the one that we're mostly talking about in this workshop, although both definitions have been thrown around a bit, sometimes treated as the same, sometimes treated as different. So in this talk, I want to focus on the latter one, and I want to defend this choice a bit because I think sometimes the debates sometimes get conflated about what is at issue and what is being discussed. So I think that this is the interesting one to talk about because it's not obvious, right? Like we don't know whether neural networks are consistent or potentially compatible with this definition. So it's just interesting. I also think it is the case that, or I wouldn't say this is an opinion, it is definitely the case that this representation is necessary for certain domains. So logic, for example, is defined by this kind of a representation. So to the extent that humans do logic, we need some capacity for this type of representation. There's also the argument that we're building AI not just to replicate humans, but to do things, better than humans and different than humans. Gary used the calculator analogy yesterday. So whether or not we think humans have this kind of representation, we probably want AI to be able to represent this type of a thing. I want to throw out a personal disclaimer because there's also the question of whether or not this is needed to do to solve natural language, or whether it's the right representation of language. And that actually, I'm not sure that I believe that that's not necessarily the case. That's not really what I think this current debate is about. So I'm going to focus on this kind of formal languagey definition of composition for the reasons on the previous slide. I think a separate workshop should be held at some point to talk about whether this is the right way of, or necessary for solving language. I also want to give a couple caveats or concessions here, I guess. So when I'm using this definition, I'm using a very liberal version. I think I'm in agreement with Paul, although it's always, you want to discuss more details like this, maybe some of the weeds. But I want to just concede that we're using continuous representations. I think if you read like Fodor and Volition and these earlier papers, they're often talking about discrete representations. And so sometimes when I get into discussions about this, people say that if you're advocating for this kind of a compositional system, you're also advocating for discrete representations. I think these are decouplable. So let's just say representation should be continuous and focus on whether a system with continuous representations is compositional or not. And then I also think people did a good job talking about this already, that we can concede that this is not the whole story. So I think sometimes there's this assumption when we're talking about this kind of syntax-driven semantic composition, people say, you know, what about context? What about idioms? What about memorization? Like, obviously all those things are there. Perhaps there are some people who believe that bottom-up kind of good old-fashioned AI is the way to do it. I actually haven't met those people today. I don't think anyone actually has that position. So let's grant that. So the question here is whether somewhere in a neural network, for some purposes, we're representing this kind of, traditional formal language type of compositional system. Okay, so my question, I guess, is actually pretty similar to Dieuwke's talk in that the question I'm really interested in is whether neural networks can learn to implement this kind of a representation. And I emphasize learning to implement because I tend to focus on systems without inductive biases for doing it. So whereas Paul was talking about, how can we build a system that has this? I'm interested in the question we got at the end of yesterday, which is, would a trained system, something like GPT-3 or, CLIP or DALL-E or these kinds of models end up implicitly encoding this kind of a thing, in its learned weights? I would really like to answer the can question. I don't think we're able to do that. I think we need more theory, both on the machine learning side and the philosophy side, to answer that question. So hopefully eventually, right now, the question is, do the systems we have implement this kind of a classical architecture? Like I said, I think my talk is similar to Dieuwke's talk, but in spirit, but I think different in the conclusions, which is how do we know whether this has happened, right? And so in particular, I want to push back on using systematic generalization to do this. So I think most of the talks so far have focused on systematic generalization as the test of compositional behavior. And in particular, tests that are behavioral tests. We're looking at inputs and outputs to the model. And so there's lots of ways of defining these types of tasks, but a simplified version, we would say we're going to train on blue squares and red circles, and now we're going to test on a blue circle and hope the system says blue circle. And we would say that a compositional system does this because it breaks down the blue circle into constituent parts, here are colors and shapes, and it recombines them. But the problem is that these kinds of tests, I think, are neither necessary nor sufficient to say whether the system we're testing meets the definition that that I just was saying we're going to focus on here. So there's this sufficiency issue, which I think actually Allison alluded to and talked about it quite a bit in her talk, which is that for the systems we're interested in testing, the kind of big, really impressive systems, we usually don't have, we often don't have control over the training data, and we very often don't even have access to it. So we don't actually know what was in the training data. And because it's a behavioral test, we can't see the system either. We're just looking at inputs and outputs. So when our system succeeds in calling a blue circle, it could have been the case that the model literally saw blue circles in training. That would obviously not count. But we could also have these various kinds of heuristics that the system might be using. So maybe it's seen a lot of circles. It just assumes everything is a circle, and it's only learned to recognize color. This would still correctly label a blue circle, but it doesn't have the system that we want under the hood. Of course, we can work on controlling for these heuristics, but they could get quite complicated. We might not always be able to anticipate them. And they might actually be heuristics that exist over the kinds of concepts that humans don't readily think about. And so we might just never hypothesize them on our own accord, right? The second issue is that this notion of unseenness is actually not well defined, and there's many different ways that this causes a problem. I think Tal was about to talk about this and had to skip over some slides, or he was going to talk about some issues related to this. I want to highlight a particular one that which is that when we're dealing with these distributed representations, that our unseen inputs are really, interpolations, not extrapolations, right? So everything is represented in a space that has been learned. So maybe I've never seen blue circles, but I'm representing blue circles in the same 2 dimensions where I represented blue squares and red circles. And so maybe I can generalize from red square and blue circle, or in red circle and blue square to blue circle by saying this falls kind of in between what I have seen, and I can project into the output space. And that's actually a fine kind of mechanism for these models to use, but it wouldn't meet our definition of compositionality. And in particular, the same kind of mechanism could maybe generalize from 1 and 2 to, or from 1 and 3 to 2 by saying 2 is between 1 and 3. But this notion of between is not what we mean by compositional. We wouldn't say 2 is composed from 1 and 3 in the way that a red circle is composed from red and circle. So this kind of a system is probably going to perform very well, but it's not actually under the hood doing what we want when we talk about this kind of compositional system. And then the second set of issues comes with a necessariness of success on this task. So models that do meet our definition might still fail on this task, right? One way they might fail is that compositional systems are allowed to make mistakes. Nothing about the meaning of compositional says they don't make mistakes. So maybe this model, my model would call this blue circle a red circle, but if it does it because it thinks it's red, that's still a compositional system under hood. It just means it has bad perception. It doesn't mean it's not compositional, right? Similarly, compositional systems are allowed to be probabilistic. And actually the best kind of what I think are kind of the most prototypical compositional systems are these Bayesian systems, like, Josh Tenenbaum and Brenden might talk about, where the system has kind of symbolic representations, but is doing Bayesian inference over those. And so, for example, failing to overcome a training prior, calling this a red circle because the prior on red circle is just so much higher compared to blue circle, doesn't mean you didn't represent the correct decomposition into parts under the hood. It just means the prior won out right before the prediction, right? So again, failure here doesn't mean you weren't compositional. It just means that that your probabilities were weighted accordingly. So what we deal with when we're talking about compositionality, I think right now, is this representation versus behavior type of evaluation. And what I believe the definition of compositionality, that is the really interesting one that's usually being discussed in these kinds of workshops. This definition, I think, is really a property of representations. It's not a property of behavior. And so behavioral evaluations are interesting. We do care about what systems actually do. That's a very relevant thing to study, but I just don't think it bears on this particular question that, that we're asking, basically the consistency or compatibility of these models with a Fodor style definition of compositionality. And so I think what we need to do is we need kind of direct inspection of models representations. And there are lots of ways to do that. I want to emphasize, so again, when I talk about this, I think sometimes there seems to be this belief that when we say behavioral, what we mean is empirical, but there are such things as empirical evaluations that are not behavior. So there are lots of things we can measure about a model that are not defined in terms of its inputs and outputs. We can think about things like learning curves and reaction processing times. We have qualitative types of evaluations like visualizations and feature attributions, which can of course be quantified. And there's a lot of newer methods like kind of probing methods and interventions, pruning and splicing and freezing. I think Raphaël referred to these as mechanistic. I think that's Chris Ola's term. I really like this kind of family of tools. And this kind of work can help us get at the representation part directly and really supplement what's kind of missing from the behavioral evaluation. Okay, so in a couple minutes, I won't get to go through all of this, but I wanted to kind of give a case study of what it kind of looks like in my mind to use these representational types of evaluations to try to compare an end-to-end neural net against this kind of a framework. So this is work by my student Charlie. This will appear in Tackle. It's not on archive because I'm bad at archive, but if anyone wants a preprint, I'm happy to share. So here the task we're training various end-to-end vision models. I guess this session's actually on language, and I usually work on language, but this is a vision model. But I think of concepts as part of language. So this is a study of concepts. So here we're training a model to differentiate these 18 kind of abstract visual concepts. And they're composed of a shape and a layout and a stroke. And so the kind of compositional system that we would imagine solving this task would take these inputs, break it up into these constituent parts, so shape, layout, and stroke, compose them using, in this case, simple conjunctions. So there's a lot of stuff we're not going to get at here, but this is kind of a proof of concept. And then produce a label. And different inputs should make use of these same internal parts and produce different outputs. And so our question is whether our end-to-end neural networks are basically functionally equivalent to this type of system. And we want to do this using different unit tests that get at different pieces of the representation. So I won't go into details on all of these. The names are probably not great, but let's call them groundedness, reusability, modularity, and causality. So the groundedness test is basically what we call our behavioral test, just the system should do a good job. So I'll skip over that and say that basically the systems are good at identifying these concepts. So I can use the reusability, I think, is one of the ones that really highlights the type of test we want to run that doesn't directly get captured by the behavioral test. So here we're really interested in this part of this compositionality definition that says that, you know, these representations are intrinsically connected and they're composed of the same parts. So here I have a dex and a blick. These are both vertical arrangements of shapes. So they share this vertical constituent, or this vertical concept, right? And so what I want to see in my neural network is that verticality is represented internally in the network, and in particular that it's represented in the same way, kind of using the same, you know, physical representational matter, right, between these different things. And so I want these to be kind of identifiable and stable-ish, stable enough across inputs. And so we do this test using probing classifiers. If you're not familiar with it, the basic idea is you say, I'm going to train some small network on top of the activations or the parameters of my main network. So here I could maybe use just the dex, slup, serp. These are three of my classes that kind of delineate the layout concept. I can train a little classifier over the activations to differentiate these different concepts, these different layouts. And so what that classifier gives me is a particular linear or nonlinear, depending on the classifier, combination of weights at a given layer or parameters at a given layer that kind of capture this distinction, capture this concept. And then what we're interested in is whether this classifier will generalize to new inputs. So in this case, we've trained the classifier in the context of smooth circles, and we're going to test it in the context of squares. And if it performs well, that's saying that the piece of the network that was used to signify ring in the first context is the same piece of the network that's being used to signify ring in this other context. And so it doesn't mean that I have a discrete representation of ring in the network. I'm not necessarily requiring that there is a ring neuron that's on when there are rings and off when there's not. But it does mean that there is it's discretizable, right? So if needed, I could collapse this. It would be a lossy mapping, right? There's more information in continuous space than in the discrete space, but I could collapse it as needed, for example, to assign a word to a concept or to behave as a discrete system if I needed to. And basically on these tests, all of our models are succeeding. We can also look at the modularity question. So this is, I think, not quite as rich as the kind of role binding stuff that Paul was talking about, but I think is kind of a precursor to this, which is that we need to represent this idea of kind of slot filling. Like we want to be able to decouple when we're composing these parts together. We need to be able to pull out which piece is in which slot. And we should be able to remove, for example, the shape slot without hurting the layout or the stroke slot. And we can test this kind of a thing similarly by basically using our same classifier and using the ablation process. We've played around with multiple of these. This one is called iterative null space projection. It's a linear method. It has its issues. It works well for this. I won't go into the details, but the idea is we can train this classifier and then we can ablate the direction in space that was identified by the classifier. And then what we would hope to see is that we get this kind of empty space in our representation. So my representation of Blick should have, it should preserve information about the squares and the smooth stroke, but it should now not contain information about layout. And what we should see there is that our predictions and our classifiers follow through. I'm just, in the interest of time, not going to go into empirical details, but this test checks out as well. And then finally, there's a lot to say about the causality test. So I'll say that what we want to see in the causality test is basically that the representation of the parts are kind of causally implicated, not kind of, are causally implicated in the representation of the whole. I think we talked a bit about constituents yesterday, and I think this is a really interesting topic to talk about. So here we're kind of using the co-tokening or something definition as saying there should be a causal connection, like you can't think about red circles without having thought about red and circles. And there should be a causal connection between those. If I prevent you from thinking about red, you can't think about red circles, right? So there's actually a lot of mud in these results. I'm just going to skip over it because of time. I would love to talk more to other people, but I guess kind of using language from yesterday, if I were placing bets, I'm optimistic we're going to get positive results on this once we fix some methodological issues. Okay, so I guess for discussion, I think the main point that I would want to make or argue for is that the neural network representations are points in space, but I think it's kind of naive to treat them as just that kind of similarity in between figure that I had at the beginning. And actually, we can think of these points in space as quite rich. They can be understood as structured representations, and they can contain things like reusable constituent parts that can be manipulated, similar to how we would think about a kind of traditional system. But determining the exact form of those representations and making real claims about this and measuring them up against different theories of compositionality requires a lot of measurements that are not just behavior. And so I think the kind of real work that needs to happen is both methodological development. So we've started seeing really exciting work on these various probing methods, intervention methods, other kinds of mechanistic studies of neural networks. And I think that's really what needs to happen, right? We need a way of getting inside there and looking at what's happening and running, causal tests. But I also think that we don't want to be, we want to be really rigorous with this. So I think there's just a lot of work that needs to happen in vetting one another's methods. So we can't just take everything that comes out of them as truth, right? Like it's going to take some time to invent new tools and make sure that they're sound and they're reliable and they're reproducible and that we trust what we're doing. I also think there's really important theoretical work that still needs to happen. I don't think right now when we say are our current models compositional, it's a matter of just aligning the current models to existing theories of compositionality. I mean, obviously people on this panel have been doing this for a while, so they can say what I'm missing. But my understanding is the earlier debates didn't anticipate the models that look exactly like the ones that we have. And so the definitions and the arguments that exist might be underspecified in ways that now need to be more clearly specified, or might have made some assumptions about things that would necessarily go together that no longer go together, et cetera. So I think there needs to be some refinement on what we mean by compositionality in order to then answer the question of what the current, whether or not the current systems are compositional. All right, like Dieuwke, I would like to thank all of my students. I only talked about Charlie's work, but I've got a ton of really incredible students working on topics related to this. So I want to show their beautiful faces and give them a shout out as well. And thank you.
Thank you so much, Ellie. So our final speaker is Brenden Lake. Brenden Lake is an assistant professor of psychology and data science at New York University and a research scientist at Meta AI. He received his PhD in cognitive science from MIT in 2014. Brenden is a recipient of the Robert J. Glushko Prize for Outstanding Doctoral Dissertation in Cognitive Science. He's a MIT Technology Review Innovator under 35, and his research was selected by Scientific American as one of the 10 most important advances of 2016. Brenden's research focuses on computational problems that are easier for people than they are for machines, such as learning new concepts, creating new concepts, learning to learn, and asking questions. Brenden, the floor is yours.
All right, slides look okay? All right, thank you very much, Gary and Raphaël, for hosting this fascinating workshop. This is a really great group. I'm going to talk about human-like compositional generalization through meta-learning. First, I want to mention my collaborators. I started this line of work with Marco Baroni and Tal, who we heard from earlier, also collaborated on the behavioral experiments. So it's been 35 years since Fodor and Pavlick's article that launched the debate about neural nets and compositionality, and I think it's a credit to their foresight that workshops like this are still happening today. We're still having this debate. So here's my restatement of Fodor and Pavlick's systematic compositionality, maybe emphasizing a different aspect than Ellie just did. Systematic compositionality is the algebraic capacity to understand and produce novel combinations from known components. And of course, Chomsky, Montague, Gary, many others have written a lot about these ideas. And I'm interested in the behavioral consequences in particular, as maybe a slight contrast with Ellie. So I'm going to give you a behavioral demonstration. So imagine I teach you how to DAX, and maybe I'll even give you a live demo. So this is how you DAX, all right? Now, can you DAX twice? Can you DAX while jumping? Can you DAX wildly around the room? So due to your compositional skills, you should be able to understand and produce the appropriate set of actions to follow these different instructions. But Fodor and Pavlick argued that since neural nets don't have this type of systematicity, they're not a viable model of the mind. So they really did have a very strong claim there. And it was very controversial in its day, as I understand. And there's been a lot of pushback in different directions, including challenged by work like Paul's work that he talked about yesterday. But in the age of deep learning and all the amazing things that NLP systems are doing, it's certainly timely to reevaluate Fodor and Pavlick's arguments. And there's been a whole bunch of recent benchmarks looking at modern deep learning models and testing these types of issues, some of which I've been involved in, like SCAN and others like Closure, DBCA comparisons, COGS, which Tal talked about, GScan, PCFG set, and the MMT challenge, which Dieuwke was talking about earlier. But clearly from this list, you can see that you need a memorable acronym to contribute a benchmark for this. But in general, what do we find? Somewhat surprisingly, despite the amazing things that NLP systems are doing today, they still struggle on test systematicity. So this debate continues. So what I'm going to cover today is, first, I want to talk about some behavioral studies for comparing humans and machines side by side on the same test of systematicity. I think this is importantly needed, so we're going to do that. And then I'm going to talk about an approach that can help you build a neural network that achieves human-like systematic generalization through an optimization procedure that encourages systematicity. So that's going to be the key. So let's jump into the behavioral studies. So the DAX example that I started with suggests that people are these highly compositional systematic learners. But of course, that rests on a thought experiment. It relies on your knowledge of English. And many classic papers also have arguments like this. So here we developed a few-shot learning task that uses a seek-to-seek problem to probe compositionality. So a seek-to-seek problem is a paradigm for machine learning, basically means sequence in, sequence out. And this allows us to build on a powerful machine learning toolkit. But here people and the models are given just a few training patterns. So it's unlike the thousands that are usually in larger scale benchmarks. It's not enough to train a standard neural network. So what we came up with was this. The instructions are provided as pseudo words, and the responses are abstract outputs, basically sequences of these colored circles. So you might get some support or training data, like you see at the top, where you're told that DAX is red and ZUP is yellow, and LUG is blue and WIF is green. And maybe some compositional examples. So LUG Blicket WIF is blue, green, blue, and WIF Blicket DAX is green, red, green. And then you're asked a new question: how do you DAX Blicket ZUP? I'll give you a moment to look at the data, see if you can think about the right answer here. Participants had as much time as they want. Maybe if you know the answer, you can type it in the chat. If there's any brave responses. If not, I'll show the answer in just a second. So a DAX Blicket ZUP. Oh, yeah, they're good, very close. Oh, brown, yeah, so I think exactly right, when Tau. DAX Blicket ZUP is red, yellow, red. So it turns out the rule here is when you blanket something, the blanket's it's like the function here. First you dax, which is red, and then you zup, which the last argument, which is yellow, and then you dax again, which is red. It's kind of like the dax is surrounding the zup. And here's the complete support of the training set, and also the queries of the test that we gave people, borrowing this terminology from meta learning, which is going to hint at where we're going. The support had these 14 patterns that people had to learn from, and then they were asked queries that involved applying a function to novel input variables or composing functions together in new ways. And here's just the design of the behavioral experiment very quickly. There are these 4 primitive instructions, just one word mapping to single outputs. And there are these 3 functions. Fep is like thrice, so when you dax fep something, you dax, 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 or red, 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 or lug fep is lug, 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 or blue, blue, blue. Then there were 2 types of conjunctions that took 2 arguments. Blanket was like surround. We did this one together as a demo just a couple slides ago. And dax, kiki, lug over here is you concatenate dax and lug, but in the opposite order. So lug, you do the last argument first, blue, and then the first argument last, red. There was no scope ambiguity if you paid close attention to the training set. And basically, you told participants just learn a set of commands and their corresponding outputs, and they produced the outputs. They actually had to generate it. They didn't just classify it. They had to generate it by dragging these little colored circles into the array. The curriculum learning was important, so they learned the functions and then how to compose them. And they also got to look at the support set while making the generalization, so that was the setup. And in terms of the overall level of performance, how systematic are people really on these types of tests? In terms of applying a function to novel input variables, people are around 84% correct. And in terms of composing functions together in new ways, they were still good, not quite as good, but 76% correct. And here, they were actually asked to generate longer sequences than they had seen during training, more functions composed than they had seen during training. And these turn out to be major issues for neural sequence models when they're trained, but people are able to do this in this task. So let's zoom in on one of the functions. So this is the one we did together as a demo, dax blankets up. Red, yellow, red was the right answer. So 85% of people, when they had unlimited time and study, were able to do that. But the mistakes were actually quite interesting and suggestive of certain inductive biases. So a representative mistake here was red, green, yellow. And some people seem to translate in sort of a one-to-one way. Maybe you felt like you were trying to do this during the demo where first, okay, what's a dax? So I'll go and look it up, it's red. And here's up at the end, I know that one is yellow. So red, it goes at the beginning, yellow at the end. And for the middle, I can't quite figure out what it is. Maybe I'll just grab something that aligned with it previously. So this is like one-to-one, left-to-right translation strategy. Here's another test example with kikis up. So for this one, the kikis here, so that means you do the last thing first. So first you zup bep, which means 3 zups, 3 yellows, and then you go back and you whiff, which is green. So 85% of people were able to do that. And a representative mistake actually was to forget to do the last thing first and the first thing last. People prefer to do the first thing first, not unreasonable. So they seem to have some type of iconic concatenation bias that was also showed up in their mistakes. So to summarize, we found some hints of inductive biases. We're going to dive into these more in a second. One-to-one. So if you don't know the meaning of zup, you probably think it's like 1 symbol rather than 2. Or if you don't know how to dax zup, you probably should dax first and then zup. That's some type of iconic concatenation, or I'm going to abbreviate it with IC. Now, rather than just being quirks of this task, I think these types of biases, one-to-one and iconic concatenation, have really interesting parallels in natural language that we could dive into in the discussion, but I won't have time to do that right now. And the second experiment, we dug deeper into these biases in a more direct test, and rather than have people learn some algebraic system, we gave them a very open-ended task. And we basically just said, all right, perform a seek-to-seek task. Like it would be funny to ask a neural net to do this. Perform a seek-to-seek task with no training data, just guess. Okay, so the same instructions as before. These are commands, and the goal is to guess their outputs. You have these different colored circles to make sequences. So what's a zup? What's a zup zup? What's a dax zup? And they had to like fill out this worksheet just with their intuition. And it turns out that people produce very structured responses. again, with no evidence of what to do in particular, right? 60% of people responded basically in this way, showing the 3 inductive biases. They basically assigned one color to each word, translated left to right. And they also follow mutual exclusivity, which is an inductive bias from developmental psychology and word learning, basically meaning that if you don't know what zup is, assign it a new meaning rather than just another word to refer to something else. So 60% of people were completely consistent like this. And then the other 40% did sort of interesting variants. Here's somebody over here that basically did the same thing as most people, except they assigned the number of colors based on the number of syllables in the word, which is kind of reasonable. Here's a response that had some structure to it, but was much less structured. Like you can't actually find a consistent symbol that DAX was mapped to, although it was mapped to yellow more often than the other things. So people had a fair amount of variability, but certainly we found evidence for those heuristics, those inductive biases. Okay, so what have we learned so far? And the most common human response is fairly algebraic and systematic in the different tasks, really exactly in the way Fodor and Collision described. But people rely on inductive biases that are sometimes aligned with the algebraic solution and other times might lead them astray. And thus, I think a model, human-like model of compositionality would reflect both. So what are the goals of a model? And this is what I'm going to tell you about in the next few minutes. We want a neural network that can do few-shot induction of primitives and functions to compose them flexibly and systematically, but also prefer certain hypotheses that capture input-output regularities and heuristics that people also show. We want to model the adult compositional skills. In this case, we're going to use meta-learning to do so, but importantly, not meaning that the process by which the model comes to these skills is not supposed to model how people acquire these skills or come to these skills. We can also talk about that in the discussion. So how do we do this? We're calling the approach behaviorally informed meta-learning, or BIML. And it's also using transformer architecture. It doesn't necessarily have to be, but a bit like Stephanie just described in her talk. The idea is that you specify desired behavior with high-level guidance and/or direct human examples. So you say, this is what I want my model to do. I want an inductive bias like this. And then you use meta-learning to guide a neural network to parameter values that, when faced with a novel task, produce human-like generalizations and can overcome some of the challenges of systematicity. So here is a sequence-to-sequence transformer. It's already been optimized. And the hope is that you could give it a query like DAX splickets up, the one we did together as that demo. It would process it and then produce the right output sequence. But alongside it, it's passed the support set, sort of a mini data set in which it can use to base its response, which is actually just this whole set that we gave to people is concatenated as a big string as context. So we're hoping it's going to look at the context in order to answer the query, but the key is how it's optimized. And the big idea is that it's optimized over a series of dynamically changing sequence-to-sequence tasks that encourage systematic generalization. There was an earlier version of this at NeurIPS in 2019, but this works much better by using the transformer. So each episode samples a latent grammar with primitives and compositional functions. So these are just generated, right? And the first episode, you get a bunch of commands for support, and then you have to answer queries. There's an underlying latent grammar for that episode, and then you throw that away and you get the next episode, which has a different sample of latent grammar, and you learn to answer those questions. So over time, the model is going to optimize for systematic generalization. The queries, it turns out we pair them both with the algebraic response about 80% of the time, and then bias-based outputs the other 20% of the time in order to mask roughly the proportion in the human data, where we then, rather than have the algebraic response, we put in one of those sort of heuristics instead. So how do people in BIML compare? After optimization, BIML's most likely outputs are perfectly systematic on the same test as people. So if you pick the most likely output sequence, it's 100% consistent with the grammar. When you sample over possible outputs rather than the most likely, the accuracy is 83% is closer to the human performance. So it has some variability in how systematic it can be. For predicting human responses, so here we can actually look at the log likelihood of the human data, both when they're algebraic, but also where they were making these more bias-based responses. Here in this table, log likelihood is used where so larger, less negative is better. A baseline model that's just guessing would have this number. If you use sort of the ground truth grammar, you get 538 the symbolic ground truth grammar with some hand-tuned like heuristics on top of it can get around -357. If you just train BIML to do algebraic generalization but without the biases, you get -455. And if you train BIML to be algebraic and also to show those human-like heuristics, you can do about as well as the symbolic model, maybe a tad bit better. So here's some examples. I'm going to show you a couple of these and then I'll wrap up. So here's DAX spliggets up. This is the one we did together. 21 participants did this, but also, some people use these one-to-one heuristics instead. The BIML models does the same thing most of the time, the algebraic answer, but then also one-to-one responses. Here's one's up Kiki DAX, where you have to concatenate, but you do DAX first, so red first and then yellow. Most people figure that out, so the model often does that, but then some people do the opposite. So they do the first thing first, and BIML is able to do that as well. Here was a longer, more complicated example. And I'm just going to quickly mention that we can also do this on the worksheet task. So we can train BIML on some participants and predict held out participants on this worksheet task where they're basically like fill in the responses one at a time is the way BIML can do this completely open-ended task with no data, with no examples, right? It sort of guesses for the first one and then feeds that in and guesses the second one and so on. And it turns out you can produce worksheets that look human-like. And in this case, we actually couldn't develop a symbolic heuristic that was nearly as good as the BIML model trained on the human responses. Okay, so let's step back and talk about where we are. We wanted a neural network that can do few-shot induction of primitives and functions and compose them flexibly, prefer hypotheses that capture certain input-output regularities that people also showed, and model adult compositional skills. And I think this approach can do that. In terms of the limitations and open questions, how can a model learn entirely new primitives rather than simply new primitive mappings? It can't handle a brand new symbol. It has to see all the symbols during optimization. This is a challenge like generalizing outside the training space that Gary has written about. I think there are ways you could address it with an approach like this, but it would need to be extended. And how do these abilities develop? How do people come to this rich starting point? Here, the model's optimized over many different artificial grammar learning tasks. People don't receive a huge number of those, but the greater principle of honing compositionality and systematicity through practice, I think, has real developmental merit, and that's also something we can talk about in the discussion. Okay, so to conclude, despite remarkable progress in deep learning, Boder and Polishion's 1988 article is still being debated today. Here, we use behavioral studies to compare humans and machines side by side on the same test of systematicity. The most common response is algebraic, but people also use inductive biases that are good heuristics, but can also lead them astray. BIML shows how you could optimize a neural net to achieve human-like systematic generalization by a procedure that encourages systematicity, using human data, and hopefully this can also inform engineering efforts to building more capable, more human-like AI systems. Thank you.
Thank you very much, Brenden. So given that we now passed the 100-minute mark, we'll just take a 5 minutes break and then come back for the discussion. All right, so I think we can start the discussion now. I want to start with something that's a running thread through all the different interventions today and yesterday to some extent as well, which is the dichotomy between the more behavioral approach and the more representational approach when it comes to investigating compositionality in these models. We have two related questions in the Q&A that I'd like to read. So there's one question from Rosa Cow that asks, is Dieuwke saying that we should take the question of whether the system is compositional to be fully settled by behavioral input-output evidence, or do we need to look inside the system at the underlying architecture? And if we are looking inside, what are we looking for specifically, empirically? And then Verna Denkers further asks, Ellie, do you think that representational analysis would also be needed to be convinced of human compositional generalization, or do similar concerns about the under the hood computation of meaning you presented apply there? And if not, why should models be held to different standards? So maybe if you, Dieuwke and Ellie, if you want to start with this question.
Yeah, maybe I can start, because I'd love to hear what Ellie has to think about this, because I think indeed my take on this is sort of that the evidence that we have for humans being compositional is like the vast majority of that, I'd say, is behavioral, because we cannot really look in people's brains, and like people have tried to find that in the brain, and it's very difficult. And I think it's also like an open question how these kind of things are implemented in the brain. So from that perspective, I would really like the second Verna's question, like why is that different for models? So I think for me, I do really like looking inside models and figuring out what's going on, but more because I'm hoping that that might teach us something about how particular things might be implemented also in the human brain, or might help us to disentangle particular hypotheses and these kind of things. But not because I think that this is the only way that we can show ultimately that models are compositional or not.
Yeah, and so I'll add to that. I mean, I would actually push back. I agree that probably most of the data we have on human representations is behavioral, because that is the easiest to collect. But I think most of the theory we have on human representations is dependent on not strictly behavioral data. So for example, things like reaction time, eye tracking experiments, like all the garden path work depends on eye tracking and reaction time types of things. Surprisal metric, right? Those types of metrics, which are not strictly behavioral. It's not just what did the person produce, or, you know, some acceptability judgments, right? But there's other kinds of processing signatures. So I guess we can debate about the extent to which that is behavioral, but then there's other strictly, so like fMRI studies have become increasingly common, right? Like looking for the parts of the brain. There's a lot of work on people with lesions and, you know, with other kinds of disorders that try to help us disambiguate. There's the work where people kind of piggyback on EEG surgeries to try to find the parts of the brain. And that stuff is like really important and supportive of theories of how language is represented and organized in the brain. So I don't think that we're holding models to a higher standard. I think we have a larger variety of tools to use with models. We're not subject to IRBs. We don't have to worry about those kinds of things. Like we can just go through and work much more, you know, we can be a little more aggressive with the kinds of things we try. But I think that non-behavioral studies are very important in cognitive psychology, neuroscience, and psychology and those types of things. And in terms of how important, I mean, we kind of take adult humans, like healthy adult humans, as like they are compositional, and it's not really up for debate in a lot of cases. Although some of these cases that then we're talking about with language, it may or may not be, you know, compositional in the Fodor sense, and that's still open. But this comes up a lot in what's called comparative psychology. So people debate, you know, what non-human animals have representations, and also in developmental psychology, when do children, I talk a lot with my colleague Roman Feynman about like negation and disjunction and stuff, right? So when do children have that? And there, you can't just ask the kid, like, do you know what not means, right? You're trying to infer. And so there you have behavioral signatures, but then you also have to look at other types of things to try to figure out what's going on. So I think it's not the case that we're holding models to higher standards. It have different sets of tools, but I think that both things are very important in order to adjudicate between these questions that are fundamentally about representation.
So we have a lot of follow-ups. Gary? You're muted, Gary.
Something has been gnawing at me all day, and it relates to this question, which is really about semantics. So part of the issue, I think, is most of the metrics that we have are on the surface form of a system. And systems like GPT-3 are pretty good at producing the surface form. We don't know what semantics they associate. In some instances, we're not even asking what semantics they associate with it. There's a way in which DALL-E is actually a better tool for investigating some of these questions than GPT-3, which is it kind of puts its semantics out there in the form of a picture. Whereas GPT-3, what it does is it just predicts more words, and we don't directly assess the semantics. And I loved Ellie's talk and the point about representation versus behavior. Part of what we do for humans is we use introspection. We know how we work. And part of it is we also see how the language aligns with the actions that somebody actually undertakes, which is also an indirect measure of the semantics. My gut feeling is that these systems, GPT-3 type systems, large language models, are pretty good at representing or at least emulating, let's say, the compositionality that you could see in syntax. But the way I try to draw the distinction yesterday is it's about deriving a meaning from syntax. And I don't think we have a lot of direct measures of that, and I'm not sure that it's there. There's another question in the Q&A, which is like, what does all this have to do with cognitive models? Well, a good language system should give you stuff you can reason over. I gave the blocks world example yesterday. So, I should be able to say, let's put the block, the red block on top of the blue block, and you should know that the red block is now on top of the blue block. If we just look at systematicity and syntax, which is important to look at, we don't get at that question about, like, what does the model, quote, think is going on in the world that this is all corresponding to? And I think we need to move towards measures that get at that in some way. Maybe that requires, next generation models that are like Gato that actually are multimodal and so forth. But until we get at what is the meaning that this model is allegedly composing, I'm not sure we're getting at compositionality in the right sense at all.
There were follow-ups from Paul and Brenden. Did you want to add something, or? No, Brenden.
Yeah, no, not really. I like Ellie's answer on this, and just that representation is really important. I also think behavior is important, and they're almost certainly correlated. So I do think we should do both. And her tackle paper looks awesome. I'm looking forward to finding it.
Okay, I see now other raised hands.
Maybe I'll make the point I was going to make, but
right.
retracted because Gary made it, but I think it deserves repetition. Foden and Pavlick were making a philosophical argument, and introspective evidence is very important in philosophy. I think it has legitimate status in cognitive science. I don't think it should be dismissed. Gary mentioned it. I just wanted to underline it. Now, what that has to do with AI is an open question, but I do think that a lot of the impetus behind believing in compositionality within our heads comes from introspection.
Alison?
Yeah, I'll be quick because it aligns closely with what has now been said, but I agree. I was just going to make the point that while a lot of our evidence from other humans comes from behavioral evidence, we have the capacity for introspection with respect to ourselves, and I think we get actually a substantial amount of evidence with respect to how meaning is derived and what meanings are like from that, and from sort of shared communication about our individual introspections. And the other was I don't think we need to or should choose between representational analysis and behavioral analysis on the models, because I think that there are sort of complementary limitations. There are important and very significant limitations and challenges on both sides, and in both cases, I think that they can be offset to an extent by also doing the other side.
Tal, you kind of follow up as well?
Yeah, my point is mostly terminological. I guess I hadn't appreciated before this discussion, but the analysis that Ellie proposes to do doesn't require generalization at all. It can be phrases that have been seen millions of times in the training set. And the important thing is that they're represented in a systematic relationship with each other. So I don't know. So that seems important for understanding the kind of theoretical stakes of this analysis, but also in terms of its practical implications for AI. So I think there has to be a bet somewhere that systems that have that systematic structure to their representations of phrases that they're familiar with will also generalize well to new phrases. Otherwise, why does it matter in practice? That's kind of a question maybe for Ellie or for anyone.
Sure, I can, I mean, so you're absolutely right. The thing I was describing, you could very well ignore generalization and just say we're going to look at known things. The maybe highly related point I would think is that is this comment of kind of you're mapping new inputs into a known representational space, which I think is true of traditional systems. So I'm thinking out loud here, but yeah, so you think of like a good old fashioned AI system, right? You're going to parse it into a known vocabulary. And I think it's similar in a neural net. You have your feature space, your learned feature space, and the new inputs are going to be parsed into that. So something about it is if you know how the known part is structured and you know how a new input is being represented in that space, you know what's going to follow through after that, right? So it is true, like you would still have to say on an held out instance, like what's going to happen here, what pieces are going to be active. And, you know, like once at layer 3, I've put it into this and I know these are the functions, the rest is going to follow through the same as it did for unseen things. Of course, we want some newness to it. You're not completely forgetting about the fact that this is new. And so some of that newness might get carried through in some other way. But I think that part of it is, or I forget who had the quote of like, you know, new things from known components. Maybe Brenden had that one. And I think that's part of what it is trying to characterize the system in a way that now if you could do this perfectly, you could say something about how it will behave on any unseen inputs, right? By figuring out how it's going to be represented at some lower level.
Yeah, Tal, you had a response to that?
Right. Yeah, I guess I think that the point that Dieuwke and Verna were making is that sometimes you want the representation of the known elements to be non-compositional, but the representation of novel elements to be compositional, because there are certain things that you just have to memorize about idioms, let's say. But that's never going to be the case, I think, for novel words, like, or novel phrases. Like your best bet for novel phrases is to just compose the meaning from its parts.
I could play like a thought experiment where that, like you have this option. So there's this kind of concept in some of these theories of concepts of like placeholder symbols, right? So like I could, in principle, hear you say some word that I'm like, I thought I heard what you said. I know that it isn't the thing that I thought it meant. So I'm just going to assume there is a thing called DAX that you just said. And now I place it into my system. And then it can still participate in all kinds of other functional operations without it actually having any semantic content at the moment. So that would allow me to treat it as idiomatic. Even if you said kick the bucket and I'm like, I know no one kicked the bucket. I have no idea what you're talking about. Clearly this is a thing. I think we're kind of capable of doing something like that. So you could kind of co-opt the idiomatic expressive pipeline for an unseen, like you could opt to treat it non-compositionally, even though it's a novel input. I don't think anything would prevent that. I don't think our neural nets are capable of doing that, but in principle, could they, like, possibly?
Right. So there is a somewhat related question from Iris Berendt, who asks, can you panelists please summarize your positions on the issues of innateness and generalizations beyond the training space? What do you agree or disagree about? Specifically, do you agree on whether generalizations beyond the training space can emerge spontaneously without innate algebraic mechanisms? And B, is the answer an unqualified yes or no, or it depends, for example, on the type of structural generalizations? Anyone wants to start with that?
I mean, I can start with a strong view and people can disagree just to get rolling. My view is that systems like DALL-E do not really represent the compositionality of meanings from their parts, that they sometimes get it, but they're closer to keyword search kind of level of things. That's not quite right. And that they're not innately constrained enough to represent the right underlying structures in order to do so. I think you could make an argument that there's reasonably good generalization of syntactic form in large language models. And on the semantic side, in a way, I don't think we really have the right measures. We can't, we can only indirectly ask, what does a model think of a sentence? So you can say, you know, there are three boxes on the table, and you can't get out an output the way you would in a classical AI system, where you would see, okay, here's the representation of the boxes on the table. Instead, you have to ask a question like, okay, what happens to the boxes now? Are there more boxes on the table? And so you kind of can play 20 questions with the systems. I'm not sure anybody's even done that systematically enough. I gave an example that Ernie Davis created the other day in this context, which was like the second red item or something like that. Was a little bit of tricky compositionality, and the system failed in N of 1. You know, it wasn't a systematic test, it was just kind of a little a teaser. My guess is that we don't have the semantics consistently of the cat is on the mat versus the mat is on the cat, that it's going to be confounded with all kinds of things about the probabilities of cats being on mats in the sequences, and that we're not going to see that systematically represented. But in any case, I haven't seen the test that would convince me that these systems can do that in any reliable enough way. And the ultimate thing that people have tested is really reasoning, right? The reason, and this relates to the number one question here, what is the relation between compositionality and world models? Well, it's really reflected in reasoning. When you hear the cat is on the mat, you should build a model of a cat on a mat. And when you hear the mat is on the cat, you should build a model of the mat on the cat, and then you should be able to reason over it. The closest tests I know of that are these kind of word problem tests that people have been doing recently. And you get to like 65% or something like that, which I think is impressive, but doesn't, to me, reflect that the semantics are necessarily properly represented, although there's a lot of stuff all kind of twisted together.
Dieuwke.
Yeah, thanks, Gary. I think that's a very interesting answer, and I definitely second that we need better methods to evaluate these kind of things. One thing that I wanted to point out is that I think that like these models evolving so much and getting so much better at these kind of things also really points to the fact that maybe we didn't have so super clear, or it's like I also said in my talk, like we have some idea of what it means to understand sentences and to understand the world, but we're very limited in actually translating that into tests. And an example that I like giving on that side is that I think it was like, I don't know, not even 10 years ago, that with neural networks, distributional, semantics, blah, blah, people were saying, okay, these models will never be able to understand that bananas are yellow, because those are not things that people are saying. So that's not something you can infer from a text. And now, obviously, these models do, but it's not that it makes us convinced that they actually understand these kind of things. Like we just realized that our proxy, or our like the way that we thought we were going to be convinced that models understand, it has to be updated when newer models are coming. And this also relates very much to what Ellie was saying before that. I think on many of these things, like when people were writing these things down, we weren't really prepared for what was gonna happen with the models. So for me, I think that is like the ultimate very interesting question, is that they kind of really keep pushing us to come up with better ways to evaluate these things. And to be entirely honest, I am absolutely unconvinced that whatever test is out there that we say now, okay, if they can do that, we're convinced that they can understand the world, that we will actually, or we, I don't know, I'm speaking as some sort of collective, like, I don't think that they will convince everyone that models have understood the world if they have passed those tests, because I don't know, we will probably realize that there is something else that they're still missing. And that is something that for me is actually really exciting about these neural networks, because they really push us in that way to be more specific about what we actually mean and what is actually important when it comes to language and understanding.
Brenden?
Yeah, bunch of great points. It sounds like the questioner wanted us to also come down like specifically on innateness, which I think is interesting and tough to do. So just to relate it back to some of the things I was talking about, and in that case, we were studying adults who come into the lab. And so these are adults, so they have a lot of experience, of course, and they can do amazing things with compositionality. You can give them this funny task, and you know that I think it's impressive what they can do. I don't know exactly how those adults get there and get those skills. So what we focused on was just trying to get a model that can get as close as possible in terms of the skills, maybe in a different way. And once we're there, it's going to work backwards and try to figure out, you know, a story for where it comes from. I do think learning is going to have an important role. Just if I had to place my bets, I think some aspects of it can be innate or could be part of the architecture before it gets there. But I think there's some hints that learning, like a pressure to generalize compositionally, really could help throughout the learning process, and that like infants don't seem to be born with adult-like compositional skills, at least from the studies I've seen. Like Steve Piantadosi and Dick Aslan have some really interesting studies to show there are differences between infants and preschool kids. Children seem to get like better at learning words all of a sudden, and they sort of learn how to learn words. And I think that learning to sort of compose words may be playing a role in that. And for a lot of other aspects of learning highly algebraic, systematic type of reasoning that we do in math and logic and so on, that is obviously learned, and it's really hard to learn, and we need school and many years and instruction to get those things. So I think together, like there's a good case that compositionality could be developing with experience, because there's good reason to. The world is often compositional, and it means that you're a faster, more efficient learner. If you can learn something new and use it right away in different ways, that's going to be an advantage.
Ellie, you got to follow up on that.
Yeah, I wanted to, so the question was explicitly this come down on the innateness emergent kind of question. And I think something that is like helpful to think about it, or good to think about, is there's like the innateness, like in what is a human born with. And then there's like innateness that we're dealing with in neural networks, which is, I guess, the architectural biases. And so sometimes I hear the parallel between pre-training and evolution rather than pre-training and child learning, right? And so you could imagine something where the inductive biases that we're saying are necessary to learn the way a child learns are going to be, you know, architectural inductive biases, like which nodes are connected to which other nodes, like with what kinds of existing weights, and that can be the output of pre-training, right? So so I don't think it's incompatible to say these things are learnable from tabula rasa type of network, and also innate in humans, right? Like those are, I think, compatible states, like those can both be true. And I think it's a worthwhile endeavor. Like given what we see models currently doing and the impressiveness of them, I think it is plausible that they're able to learn this kind of structure from a lot of data, probably with different kinds of learning algorithms than they possibly have in this kind of, you know, evolution proxy type of way, right? So we're going to have some kinds of sub-networks that are specialized to do certain types of things. And that might be the artifact of learning lots of tasks, not just language, not just reading the internet many, many times. But I just did want to emphasize that I don't think saying that certain structures emerge from pre-training and can emerge from pre-training and can emerge with minimal inductive biases is equivalent to making any claims about whether or not humans have that kind of innate structure. And in fact, I would actually think that those are like nicely complementary research programs.
Yeah, that's a great point. Stephanie, you had to follow up as well.
Well, I wanted to first say that I really appreciate like the really nuanced like positions that everyone's taking. And yeah, I guess I would repeat my yeah, kind of the summary of my position from my talk, which is that you really need both the right architectures and the right training data to see any of these kinds of more interesting kinds of generalization emerge. And there's really like no reason, even if a model architecturally has the ability to support like certain kinds of generalization, whether it be like in context learning or compositionality or systematicity, like there's no reason for a model to acquire it unless there's pressure on it from the training task and from the training objective. So I think that it can be unfair to say that some model doesn't have it if, you know, the training task didn't ask that of it. And I think that's kind of the case with DALL-E. And then, yeah, I think also another point I want to make is that like these things can be super dynamic, which I think is a really interesting thing that we saw in our results. And I didn't talk about it in the talk before, but like kind of unlike humans, you know, we kind of I think Brenden was saying that, you know, children don't have like compositionality in the way that adults do, but we don't like lose it over the course of our lifetimes. But what we saw in our results were that, like, at least for in-context learning, a model can learn to perform in-context learning and then lose it over time, because over time, it gets enough training data that like a kind of like in-weights memorization is sufficient to perform well at the training task. So I think this is one way in which neural network models differ from, possibly differ from human learning.
Right. There is a related question on the developmental point from Cameron Buckner, addressed to Tal specifically, but to everyone as well. It would be useful to hear a brief characterization of how well children do at the structural generalization task and at what ages. Do we have evidence that they haven't heard the novel structures before testing? And could some kind of inductive scaffolding matter? For example, once I see an example of the leap from one dependent clause to two clauses, I can go from 2 to 3 or 5+ if writing philosophy. Tal, do you want to take that question?
Well, I'm actually not an expert on this literature, but we do have quite a few references in the COGS paper. That's I'll put the link in the chat afterwards. That's the paper that I talked about in my talk. In those studies, usually people will teach the kids a novel word, and then you in the active voice, and then they'll ask them to use it in the passive voice. You can be pretty sure that they've never heard this specific word used in the active voice before, because they've never heard it in any context before. But I don't know enough about one of the criteria, I guess, for building that data set, nudging Kim, who is the person who did most of that project, really insisted on, was to only use phenomena that are known from the human developmental literature that children are able to generalize. The other thing that I would say is that I don't always know if that's relevant, the kind of developmental trajectory of these behaviors and what we want from the kind of endpoint of a neural network model. I mean, it might be relevant. I think it's, for cognitive modeling, it's really interesting to have the neural network follow the same developmental trajectory as the children, but I'm not sure that that is a requirement for having a compositional system that at its end state is even equivalent to the human one. So, but it's an interesting thing to think about.
Right. Gary, you have a follow-up on that?
Yeah, I mean, my early career was actually doing language acquisition rather than neural network models, though a little bit of Hupkes models. The most interesting paper, I think, in this connection is called Language Acquisition in the Absence of Experience. It's by Stephen Crane in BBS, Behavioral and Brain Sciences, in 1991. And he did a series of experiments that you can't quite adapt to the current paradigm, but maybe you could to the Gatto-like paradigm, where there's a bit more of a world around there. He did elicited experiments where he would try to get people to talk about situations using grammar, people, 3-year-old children, using grammar that's outside their normal realm of experience. So you would make the child do something like ask a Jabba the Hutt question about somebody else and whether they're running. And it was addressed to Chomsky's old thing about structure dependence versus structure independence. And he found that the 3-year-olds could produce questions that had a grammar that was very different from what they normally produce. The experiments were very elegant because they looked at the presuppositional structure of the language that was being talked about in order to force the kids to say things that they don't usually do. And I think it would be cool if we could take some of that kind of careful methodology that Crane used, in which you elicit a description of a scene, and the pragmatics require you to use a grammar that's not probably in anybody's training set, or at least not very common in anybody's training set, and see what you get. Now, again, that requires connecting to a world model rather than just having sentences in isolation. But hopefully we will move towards models that allow more connection to world models, as Gatto, for example, does. And then we might be able to do some pretty interesting experiments modeled on that paper, which we'll put in the reading list.
Paul?
Yes, I wanted to go back to Iris's question about the role of innateness in compositionality. I think I have found it very difficult to think about innateness questions in the context of neural network models, actually. I think it's a special property of symbolic models that you can actually think about that question clearly. So if your model of language of grammar acquisition is that you start off with a space of possible grammars that you're going to search to try to find something to explain the data, then you have a nice clean separation between what's prior to the data and what is a consequence of the data, namely the search and where you land. Or if you have a Bayesian model and you have a clear prior over some symbolic representations, then you have a clear question about what's in the prior or what's in this search space. These things make sense to ask independent of the data. But with learning models in neural networks, I think it's really fraught to try to do that. A working definition of what it means to have a bias is what a learning system will, how it will behave given ambiguous evidence for making that extrapolation. So it will choose to do A rather than B, even though both are in some sense equally fit the data. And so then it's an empirical question what these models actually do, and that's how you find out what their biases are. And a lot of people do that. We don't know what the biases are in the way that we do know what a prior is in a Bayesian learner. We don't know what the biases are. It's an experimental question. And then when we find out the answer, it's in terms of, well, here's how it behaves. When it could have behaved that way, it actually chooses to behave this way. And that's the kind of bias it has. But where does that bias come from? We don't know in the same sense that we know about a prior or a search space in a symbolic learner. So I think the question is of what the learner gets from this set of nodes and connections that it's born with in the way of how that's going to push its decisions when the evidence is ambiguous, let's just say, is really very difficult to understand. And so I think that the question is no longer as clear and useful as it was before. I think it's much more flawed. And so I just wanted to put that opinion out there about this question. I mean, it has been a very important question historically. I think it is now really muddied. And so I just wanted to put that out there.
I agree with Paul there, and I'll put it in a slightly different way, which is that what a neural network is a learning system with a bias that really is its innate bias, but that learning system is basically a function from training sets to approximators of particular sorts. And because the space of training sets is so vast, even for one particular bias, it's difficult to understand across all of that training set, all of those training sets, what the space of approximators you're going to wind up with is. And so RNNs are a different kind of way of going from data to approximators than transformers are. And across many data sets, you're going to get many different things. So you can make some real clear statement of fact, like the innate architecture here is a transformer. The innate architecture here is an RNN. And you can fill in a bunch of details about a number of nodes that are used and how many layers and so forth. And that is a clear innate system there. But what you really want to know about is, say, behavior with respect to syntax or semantics, and that is conditioned on the data. And that's the kind of complexity that Paul is worrying about. And, you know, Stephanie's whole talk was around that in a certain sense. Is like, you can wind up with a different approximator given a different data regime, even if you hold the architecture constant. And so it does make it in the end case, really hard to understand, except by doing the empirical work that I think Paul is alluding to and Stephanie was doing.
So we only have a few minutes left. Paul, yes, you want to follow up on that?
Having said that, one of the main points I was trying to make in my presentation was that I think we need to build in certain mechanisms into the architecture to promote a compositional bias. That's a hunch. I have no idea whether it's necessary and even yet whether it's sufficient. So I think there is a place where we can craft things in neural network terms that we can interpret in compositional terms. And so I think there is a way to do something like put a compositional bias in, and that's what we're trying to do.
Dieuwke?
Thanks. I wanted to follow up to what Gary said and also about Stephanie's work. That I think I find it really interesting to say that it's, well, maybe you're not saying it's just about the data. Stephanie definitely is also saying that it's about the architecture. But the question, more general question that I have is, I wonder to what extent this is also true for humans. And what I mean with that is that, of course, there is definitely like a similarity in the type of input that humans receive when they grow up. But at the same time, there is a vast difference, for instance, across cultures on like how children are treated. Like in some cultures, there's a lot of interaction with children. In other cultures, children, like they're not really spoken to. They're just picking up language from hearing what other people say. And when it comes to bias, it seems to me that like there must be something that kind of corrects for that and make sure that still we all end up at least at some point that we can understand each other. I mean, I won't claim that we all acquire the exact same system. So I'm probably not a question to ask with 2 minutes left, but I was curious what you all think about that.
And although presumably something like Zipf's law holds across different languages, right? But yeah, but Brenden, do you have a follow-up on this?
Not directly to Dieuwke's point, but I just wanted to agree that yes, neural nets are not explicit about their innate or prior knowledge, but I wanted to just highlight that meta learning is like a really new, exciting tool for cognitive science and getting at these types of questions like compositionality and the way Stephanie was using it and the way we're trying to use it. So not only is the inductive bias the neural net has in its architecture, but then you can train it to have an inductive bias. And you can actually train it to have a bias that would be too subtle, too complicated, too hard for me to write down in like a structured Bayesian model. So it's just a new tool that I think maybe can let us get at these questions in a different way.
Stephanie?
Yeah, just to really quickly answer your question, Dieuwke, yeah, I do think that like Raphaël was saying, a lot of these properties are super universal, not just in language, but in like, you know, a lot of our many different aspects of like a human's experience. And then I would also say that, but there are people have found effects of, for example, you know, in certain Eastern cultures, there's more emphasis on contextuality. You could call that like top-down is maybe more over like compositionality, and people do find cultural differences here.
Right, thank you. We've hit the 2:30 p.m. EDT mark, so maybe we can wrap up here, unless you have a very, very quick point, Gary, that you want to make.
I guess it's sort of a wrap-up point in a way, which is that, yes, I think we all 9 of us agree we need a compositional bias, and we're really struggling with whether that is a structural property of a system which could be a neural network, a hybrid neurosymbolic system, or whether it's something that emerges from the data or the format of the training regime, or all of the above. I think that those of us who are nativists have always been impressed by what Dieuwke just mentioned, which is that so many children learn the language from such different backgrounds. And so this is why we don't want to put everything on the data. But I think that is the question that the whole workshop has really been around. It's like, we're all in agreement, we need something at least like compositionality. Nobody made a strong argument against it. I think we're mostly in agreement, we're not really quite there yet. And so we're all struggling with what is the way to go a little bit further. And maybe that's a good note to end all of this on. We thank everybody in the panel for coming on quite short notice. It was a spectacular panel on, I don't know, a month's notice or something like that. We thank the audience for fabulous questions. We will put all of this online. My feeling is that it would be worth watching again because there were so many points so dense. I know I didn't get them all. So thank you all very much.
Yeah, thank you, everyone. That was really fantastic. And so, as Gary mentioned, we will put the references online on the website. We will keep the website online with the videos and for the speakers willing to share also the slides. All right. Thank you, everyone.
Thank you.
Bye.
Thank you.
Bye.